Welcome back to our channel where we explore the fascinating world of STEM. Discover remarkable scientific discoveries and innovations that shaped our world and explore the stories of brilliant minds who made them possible. Our goal is to inspire a love of learning and passion for STEM while broadening your horizons and deepening your understanding of the world. Come with us and explore the wonders of science, technology, engineering, and mathematics. Avogadro's gas law is a fundamental principle in the field of thermodynamics and is crucial in understanding the behavior of gases. This law describes the relationship between the volume of a gas, its temperature, pressure, and the number of particles present in the gas. This thesis provides a comprehensive overview of Avogadro's gas law, including its history, definition, and applications. The experimental methods used to determine the law's accuracy are discussed, as well as the relationship between gas behavior and molecular theory. The thesis also provides an exploration of the importance of Avogadro's gas law in various fields, such as chemical reactions, the behavior of gases in industrial processes, and atmospheric science. What is Avogadro's gas law? Avogadro's gas law, also known as Avogadro's law or the Avogadro's hypothesis, describes the relationship between the volume of a gas, its temperature, pressure, and the number of particles present in the gas. This law states that, under constant temperature and pressure conditions, the volume of a gas is directly proportional to the number of molecules or atoms of the gas present in the container. In other words, if the number of particles in a gas is doubled, then the volume of the gas will also double, provided the temperature and pressure remain constant. The history of the discovery of Avogadro's gas law can be traced back to the early 19th century when scientists were investigating the behavior of gases. The concept of a molecule, or the smallest particle of a substance that retains its chemical properties, had not yet been fully developed. In 1811, an Italian scientist named Amedeo Avogadro proposed a hypothesis that equal volumes of gases, under the same temperature and pressure conditions, contain the same number of particles. However, this hypothesis was not widely accepted until years later. It was not until the mid-19th century when other scientists, including Robert Boyle, Joseph Louis Gay-Lussac, and John Dalton, had further developed the concept of the molecule that Avogadro's hypothesis gained wider acceptance. In 1858, the French chemist Stanislas Cannizzaro presented a paper on Avogadro's hypothesis, which helped to solidify its acceptance in the scientific community. Avogadro's gas law is formulated as follows: V equals knots, where V is the volume of the gas, N is the number of particles in the gas, and K is a constant that depends on the temperature and pressure of the gas. This law is based on the assumption that the gas particles are in constant motion and do not interact with each other. The significance of Avogadro's gas law in the field of thermodynamics is immense. This law is essential in understanding the behavior of gases, including their expansion and compression, and is used in the calculation of gas properties such as density, molar mass, and partial pressure. It is also crucial in the study of chemical reactions involving gases, as it helps to determine the stoichiometry of the reaction and the volumes of gases involved. Overall, Avogadro's gas law is a fundamental principle in the field of thermodynamics that describes the relationship between gas volume, temperature, pressure, and the number of particles present in the gas. Its discovery and formulation have contributed significantly to our understanding of gas behavior and have paved the way for advancements in various scientific fields. Theoretical background. Avogadro's gas law is based on several theoretical concepts related to gas behavior, pressure, temperature, and molecular theory. Gas behavior. Gases are made up of tiny, fast-moving particles that are in constant random motion. These particles can be atoms, molecules, or ions, depending on the type of gas. The behavior of gases is governed by the principles of kinetic theory, which describe the motion of particles in a gas. Pressure. Pressure is a measure of the force per unit area that a gas exerts on the walls of its container. The pressure of a gas is determined by the number of gas particles present in the container, their speed, and the frequency and magnitude of their collisions with the container walls. Temperature. Temperature is a measure of the average kinetic energy of the gas particles. The higher the temperature, the greater the kinetic energy of the particles and the faster they move. Temperature is directly proportional to the average speed of the gas particles. Molecular theory. The molecular theory of gases explains the behavior of gases based on the motion and interactions of the gas particles. This theory assumes that gases are made up of large numbers of small particles that are in constant random motion, and that these particles have negligible volume compared to the volume of the container in which the gas is held. The molecular theory of gases also assumes that the particles in a gas do not interact with each other, except during collisions. The mathematical relationship underlying Avogadro's gas law is expressed as V equals knots, where V is the volume of the gas, N is the number of particles in the gas, and K is a constant that depends on the temperature and pressure of the gas. This relationship can be derived from the ideal gas law, which is expressed as PV equals nRT, where P is the pressure of the gas, V is its volume, N is the number of moles of the gas, R is the universal gas constant, and T is the temperature of the gas in Kelvin. Rearranging the ideal gas law to solve for the number of particles gives the following equation. N equals nR. where Na is Avogadro's number, which is approximately equal to 6.02 times 10 to the 23 particles per mole. Substituting this equation into the ideal gas law yields PV equals nKT, where K is Boltzmann's constant, which is approximately equal to 1.38 times 10 to the minus 23 J/K. Rearranging this equation to solve for volume gives V equals nKT P. Substituting n equals Na into this equation and simplifying gives V equals NNAKT P. This equation can be further simplified by defining a constant K equals NAK R, which gives V equals nRT P. This is the same relationship expressed by Avogadro's gas law, V equals knots, where K equals nRT P. Ultimately, Avogadro's gas law is based on the principles of kinetic theory, molecular theory, pressure, and temperature. The law describes the relationship between the volume of a gas, the number of particles present in the gas, and the temperature and pressure of the gas. The mathematical relationships underlying the law are derived from the ideal gas law and the molecular theory of gases, and involve Avogadro's number, Boltzmann's constant, and the universal gas constant. Experimental methods. Experimental methods have been used to determine the accuracy of Avogadro's gas law for over 2 centuries. In the early 19th century, experimental methods involved measuring the volume of a gas, the temperature and pressure of the gas, and the number of gas particles in the sample. This was done using simple laboratory equipment, such as glass tubes, thermometers, and barometers. One of the earliest experimental techniques used to determine the accuracy of Avogadro's gas law was the method of isochoric measurements, developed by Amedeo Avogadro himself. This method involved measuring the volume of a gas sample at a constant temperature and pressure and then increasing the number of gas particles in the sample while keeping the volume constant. By measuring the pressure of the gas before and after the addition of particles, Avogadro was able to demonstrate that equal volumes of gases under the same conditions of temperature and pressure contained the same number of particles. Later experimental techniques involved more sophisticated equipment and methods, including the use of gas chromatography, mass spectrometry, and X-ray diffraction. These methods allowed for more accurate measurements of the number of particles in a gas sample and the determination of the molecular weight and structure of the gas. Sources of error in gas experiments include experimental error, instrumental error, and environmental factors. Experimental error can arise from errors in measurement or in the preparation of the gas sample. Instrumental error can arise from errors in the calibration or accuracy of the measuring equipment. Environmental factors, such as changes in temperature or pressure during the experiment, can also introduce errors. To minimize these errors, experimental methods must be carefully controlled and calibrated. Equipment must be properly calibrated and maintained, and gas samples must be carefully prepared and measured under controlled conditions. Modern experimental techniques, such as those involving mass spectrometry and X-ray diffraction, have greatly increased the accuracy and precision of gas measurements, allowing for more accurate determinations of Avogadro's number and the molecular properties of gases. Applications of Avogadro's gas law. Avogadro's gas law is a fundamental law in the field of thermodynamics and has important implications in various fields of science and technology, including chemical reactions, industrial processes, and atmospheric science. Below are some examples of how the law is applied in these fields. Therefore, Avogadro's gas law is a fundamental law that has important applications in various fields of science and technology. By understanding the behavior of gases, we can better predict and control the behavior of gases in chemical reactions, industrial processes, and in the Earth's atmosphere, leading to important advancements in these fields. In conclusion, this video provides a comprehensive exploration of Avogadro's gas law, including its history, definition, theoretical background, experimental methods, and applications. The law's importance in various fields is highlighted, and its continued relevance in modern science is emphasized. By understanding Avogadro's gas law, researchers can gain insight into the behavior of gases and make advancements in fields such as chemistry, physics, and atmospheric science. Last, thank you for joining us on this journey of discovery and exploration. We hope you've enjoyed learning about the wonders of science and the incredible breakthroughs that are shaping our world. From uncovering the mysteries of the universe to tackling some of the most pressing challenges facing humanity, science truly has the power to transform our lives and our world. We invite you to continue exploring the amazing world of science, and to join us in our mission to promote scientific understanding and knowledge. Stay curious, keep learning, and always keep asking questions. Who knows what incredible discoveries lie ahead? Thank you for being a part of our community, and we look forward to continuing this journey together.